We are here with warm fronts, a whole different ball of wax in comparison to cold fronts. Warm fronts evolve from warm air masses meeting cold air masses, and warm air masses, as we know, are less dense, they're more buoyant, they're more unstable in atmospheres, they can rise dramatically. They are often moist, but not always moist. For instance, the maritime tropical out of the Pacific is a moist, warm air mass, and out of the Atlantic and out of the Gulf of Mexico. And during the summer only, the Mexican subcontinent brings in continental tropical air masses into Arizona that are really responsible for their summer monsoons. Now, you can imagine that their summer monsoon in Arizona is a very dry, dust bowl, haboob kind of an environment because of the impact of the warm air masses on Arizona. So we learned about the seasonal changes in winds with monsoons, and Arizona's got one as well. We are going to talk about a phenomenon called overrunning, and it is when these air masses, especially during the summer, get to be a little stronger than they usually are, and they can run over a cold front that is sitting low. Let's look into it. So we go back to our analogies, and now I've got the Volkswagen chasing after the Cadillac. Doesn't happen often, right? But let's think about a scenario and think about a story where this could be happening. Let's say a whole gang of Volkswagen Beetles decides to gang up on one lonely Cadillac Escalade. And you've got a whole entourage of Volkswagen Beetles coming after this Escalade. Well, the Escalade decides to retreat because he doesn't want to just ramrod all of these Volkswagens. He's got a heart, so he decides to retreat. But it's really hard for a cold air mass, which is so dense, to retreat. So he is retreating slowly because it's hard to reverse directions after being going 30 miles an hour and then grind to a halt and then start retreating. You retreat slowly when you're a cold air mass. It doesn't happen very often. And these little putt-putt Volkswagens are catching up to you at 15 miles an hour. And you know what? They're going to go right over you. They're just going to take the bull by the horns and drive over you at this point. And the same thing, we call it overrunning in meteorology. If you need another analogy, we'll go back to the hand, right? And there's a couple of analogies, but I'll go to the hand first on the right-hand side. So you had your Cadillac Escalade that just met a whole lot of friction, and it was moving along pretty well, but then it just stopped and stayed stable and started to reverse because it felt something was coming at them. A warm front blob was coming at them, and it smushed down the Cadillac. I know it seems you can't imagine a flattened Cadillac Escalade, but maybe you can think about it as a warm, gooey gob of honey is the warm front that is just sweetening the heck out of the Cadillac and just smushing it down into submission. So you can pick up any kind of analogy you like in order to keep the two of them in your head. What you note here is that when this warm, dense, less dense air smushes the colder, high-density air, you have a whole range of clouds in making that happen as this cold air is retreating out of the way. So you start with low clouds and then gradually move up the clump that you're smushing. And you have higher clouds after that. Let's look into it and get our heads into the warm front a little bit more and get our heads into the overrunning. The overrunning is all about the retreating cold air mass, all right, along the front line. Here's the front line, and the warm air mass is riding over the cold air mass. First with stratus clouds, then with altocumulus clouds, finally with cirrus clouds, which means that if you are banjo guy and a warm front is coming at you, you are sitting on your front porch wrapped up in, you know, a hood, and you've got a comforter around you because it's cold where you're at, sitting on that porch waiting for spring to come. And when you look up, maybe 2 or 3 days before the cold front comes through, because cold fronts take a long time to come through, you'll see the cirrus clouds. And then you'll see the altocumulus clouds, and then you'll see the stratus clouds, and you'll know that something's coming at you. But it'll happen over time. To take this from the cross section down to the surface maps, here is your retreating cold air mass and your overrunning warm air mass, with your cirrus clouds showing up first to banjo guy, altostratus, altocumulus, and stratus. If we look on a map view, we have banjo guy out here, and the warm front is coming at him from the southwest, while my cold front is retreating back to Saskatchewan in the northwest. Once you go back from whence it came, it is going to the northwest. Warm fronts are not nearly as nice as they sound. Warm fronts are associated with snow. Doesn't seem to make sense, does it? But it is. You have to think about the logic of this, and then it makes sense. The reason it's associated with snow is because you have got a lot of moisture up here that is buoyant and has been riding quite high. That is becoming snow as it moves through the colder layers of the cold front that is retreating. In fact, one of the first things banjo guy will see is cirrus clouds, then some altostratus. By the time he sees some nimbostratus, it's snowing. After it snows in the cold air, that cold air at 22, so perfect for snow, starts to become a little bit warmer because there's less cold air under the wedge and more warm air above it. Then it becomes sleet. And then as the warm front moves near banjo guy, there's even less cold air above in the wedge and more warm air above it. So this is rain. Finally, I've got a very stable atmosphere of a warm lid on top of a little bit of cold air. So I have fog in here. So as a warm front moves in, it's not as nice as it sounds because you have a whole range of very nasty precipitation. This happens over a very long distance. Look at this, 600 kilometers. The last thing we were talking about was about 50 kilometers, about 30 miles. This is about 300 miles. More like 350 miles for a warm front to come in. It takes a long time to go through that distance. This is a lot of precipitation, a lot of prolonged precipitation with a cold front, and a dramatic change in temperature from 22, where banjo guy is, to 53 and back of it. But you have to go a long way through a lot of precipitation until you get to the 53, and it does take some time. To go to the surface maps more directly now, you can look at the surface maps and you'll often see white for the snow, pink for the sleet, and green for the freezing rain. So that's what you're noting here as the front comes in. Now this is skewed, okay? So this big surface map, really, it should be tilted this way because here's your X and X, here's your P and P prime, and your P is over here and your P prime is over here, right? So this surface map should be skewed a bit to show you the rain, the freezing rain line. Let's talk about pressures. And I'm going to move this up a little bit if I can. Sorry, I'll bring this down a bit. Let's talk about pressures on the surface map. Before the warm front comes in, Banjo guy senses that the pressure is dropping. So he sees the station models showing the pressure is dropping before the warm front comes in. Well, that doesn't make any sense because he's in the middle of a cold air mass. Why should the pressure be dropping? That pressure should be rising because it's a cold air mass. But it is a cold air mass that is retreating. So here he has a lot of cold air, but as the cold front comes toward him, he has less cold air and less cold air and less cold air. So his pressure is dropping because he has less dense air around him. Important thing to think about. Important thing to know in order to plot your warm front. And in the warm sector behind the front, you notice that the pressure starts to increase a bit. The pressure drops and the pressure starts to increase a bit right behind the front. Well, why is that? Because the warm air is very buoyant and it's starting to meet the colder, more dense air that has a higher pressure. So as you get closer to the front, the pressure starts to tick up a bit because it's meeting the colder air that is more dense. It's catching up the cold, dense remnants of the cold air mass that's in here by Banjo Guy. There is no kink in these isobars. Here's the 1008 isobar. Here's the 1004 isobar. No kinks. No kinks because this is over such a prolonged distance and such a prolonged time that these pressures don't drop dramatically like they do with the very fast cold fronts. So no kink, and if you ever plot isobars, you can note, you know what, that's probably a warm front because there's no kink to it. So I'm giving you all these clues when you look at isobars carefully and when you analyze the data. Now, like we said, especially during the summer, you might not be able to think about, is it warm, is it a cold front? You don't know. Look at the dew points. The dew points will tell you a lot, especially if you're in Oklahoma or in Texas. Here's a great point of view that really speaks to tornado formation. These two air masses differ in density, even though they are both warm air masses, because their dew points are so dramatically different. This is a warm, moist dew point at 69. This is an extremely low dew point at 24. These are two air masses that are at very different densities. Which is more dense? Well, remember that nitrogen and oxygen have a heavier mass than water vapor. So if you have more water vapor in your air mass, you have less mass. Because we talked about the fact that nitrogen and oxygen are molecules that have more mass to them. If you have lower humidity, you have higher concentrations of nitrogen and oxygen, you have more dense air. This is the more dense air mass. The humid air mass is the less dense air mass. It will ride higher. Then the continental tropical out of Mexico will ride lower. This becomes really important for cyclonic development of tornadoes right in that area. We'll go into that soon. I want you to be able to find dry lines on maps. This is a dry line map. This is not a temperature map. This just looks at dew points. 68 from the maritime tropical air mass, 28 from the continental tropical air mass. This is a dew point temperature map only. These are not air temperatures. They're dew points only. Same thing here. This is a dew point temperature map only. And you see where the gradients get very tight. That's where your pressure gradients are going to be, and your temperature gradients and your dew point gradients are all very good indicators. Where we have tight gradients, we have a lot of change. Where we have a lot of change, we have a front. So there's a front line right here where all these tight gradients are. Very important to note. How do you find a front? You look for tight gradients in either isobars or isotherms or Um,